So a mole is defined as the amount of substance that contains as many atoms, molecules, electrons, ions, or any other particle in 12 grams of carbon-12.
A mole is equal to 6.022 times 10 raised to 23 particles of an element, which is also known as Avogadro's number.
The molar mass of a chemical compound is defined as the sum of the total mass in grams of all the atoms that make up a mole. This is a similar concept to the molecular mass. Molecular mass is a number equal to the atomic masses of the atoms of a molecule. However, though similar, they are entirely different matters. Here's the difference between the two.
The two approaches in seeing this is the mole and molecule approach. Let's start with the molecular mass. This unit is measured with atomic mass units or AMU. Ethanol has 2 atoms of carbon, 6 atoms of hydrogen, and 1 atom of oxygen. The atomic mass of each element from the periodic table would be carbon at 12.011 AMU, hydrogen at 1.008 AMU, and oxygen at 15.999 AMU. To find the molecular mass, we simply combine all the atomic masses of the elements. That would mean 12.011 times 2 AMU of carbon, plus 1.008 times 6 AMU of hydrogen, plus 15.999 AMU of oxygen. Combining that would give us around 46.069 AMU of ethanol. Now as for the molar mass, they're pretty similar to the previous one, but instead of using molecules, we're going to treat the numbers as moles. That would mean also using the unit of grams per mole instead of AMU for the constituent elements and for the total. This would give us 46.069 grams per mole of ethanol.
The 3 previously stated are the main measurements involved in the mole concept: the mole itself, the molar mass, and the number of particles. Manipulating these variables could be made easier with this simple triangle. The arrow says it all. To convert mass into moles, we simply divide it by its smaller mass, and to convert moles to mass, we multiply it by its smaller mass. To convert moles to number of molecules, we multiply it to Avogadro's number. And to convert number of molecules to moles, we divide it by Avogadro's number.
To make more sense on this diagram, we need to see it in action.
Suppose we have 34.2 grams of fructose and we need to know how many moles of fructose it contains and how many molecules of fructose it contains. Let's plot 34.2 grams of fructose on a side. Multiply that to the desired unit over the given unit. We'll have 1 mole of fructose on the numerator and have the molar mass of fructose at the denominator. Fructose has 12 moles of carbon, 22 moles of hydrogen, and 11 moles of oxygen. 12.011 times 12 moles plus 1.008 times 22 moles times 15.999 times 11 moles will give a total of 342.297 grams per mole. Now perform the operations and we will get 0.099 moles of fructose, which we can simplify to 0.1 moles or 1/10 of a mole. Now, to get the number of molecules of fructose, we take the mole value that we have computed earlier and plot that on a side.
Again, we're going to place the desired unit on the numerator and the given unit to the denominator. We'll put Avogadro's number on the numerator and 1 mole of fructose in the denominator. We perform the operations and we'll get 6.022 times 10 raised to 22 molecules of fructose.
Percent composition tells us how much of an element there is in a compound. To find out the percent composition of hydrogen and oxygen in water, we need to find the molar mass of water by adding the molar masses of the constituent elements. Hydrogen has a molar mass of 1.01 grams per mole. Multiplied by 2 since it has 2 atoms in the formula, oxygen has a molar mass of 16 grams per mole. Therefore, water has a molar mass of 18.02 grams per mole. With that value, we can put the molar masses of hydrogen and oxygen in the numerator separately. 2.02 grams per mole over 18.02 grams per mole and 16 grams per mole over 18.02 grams per mole. These operations would give us the values of 11.21% hydrogen and 88.79% oxygen. Let us also note that the moles of each element do not always determine which has the bigger composition. Everything will depend on the molar masses of each element. The molecular formula is a formula that denotes how many atoms of each element there are in a compound. Another similar concept, the empirical formula, is a formula giving the proportions of the elements present in a compound but not the actual numbers or arrangement of atoms. It is also the lowest term of the molecular formula. To find the empirical formula of a compound given its mass, let's say the formula of the product of mercury and chlorine with their respective percentages, we separately solve the two elements. We plot 73.9 grams on a side, since it is 73.9% of the given 100 grams, and then we multiply it by the desired unit on the numerator and the molar mass of mercury at the denominator. This will give us 0.368 moles of mercury. For chlorine, we do the same process. 26.1 times 1 mole over 35.45 grams per mole gives us 0.736 moles of chlorine. Next, we find the molar ratio between the elements. 0.736 divided by 0.368 gives us 2, which means that there are twice as many moles of chlorine as mercury. We can then arrive to HgCl2 or mercury chloride as our element.